I should also say that the news yesterday was that this object came closest to the sun, and it received a huge amount of heat from the sun. And the latest report indicates that it became extremely bright, much more than expected for familiar comets. This morning, we have a report that the object got much brighter than expected, and moreover, the color of the object is bluer than the sun. And that's very surprising, because usually when there is dust around an object, it should make it red.
The James Webb Space Telescope has just captured the first real image of 3I Atlas. The moment felt like a turning point. Every pixel in that image seemed to whisper of distant worlds, of a traveler from another corner of the galaxy slipping quietly through our solar neighborhood, and of the extraordinary possibility that we were witnessing something never before seen with such clarity. From the earliest stages of planning, astronomers knew that 3I Atlas was special. Discovered in early July 2025 by the Atlas Survey System, it became only the third confirmed interstellar object ever detected. The two that came before, 1I/Muamua and 2I/Borisov, had already expanded our understanding of what might cross into our solar system, but both had left behind unanswered questions. Oumuamua defied simple classification, while Borisov, though comet-like, still carried mysteries about its chemistry and origin. Now, with 3I/Atlas approaching, scientists prepared for a race against time and chance to catch it within the limits of observation. On August 6, 2025, the James Webb Space Telescope succeeded. Using its near-infrared spectrograph, NIR-SPEC, Webb locked onto 3I Atlas. That single observation was the product of months of delicate calculations and precise trajectory modeling. From such immense distance, the comet was a faint, moving target drifting against a constantly shifting backdrop of stars. The team had to ensure that it would fall perfectly within Webb's narrow field of view as it hurtled inward toward the sun's. Success meant more than an image. It meant capturing a spectral map of the comet's glowing shroud, the coma that envelopes its nucleus. Achieving this felt like threading a cosmic needle across astronomical distances. The image that emerged was unlike any simple snapshot of a comet. It revealed a dense, carbon dioxide-dominated coma radiating in the infrared between 0.6 and 5.3 micrometers. Within that glow, faint signatures of water vapor, carbon monoxide, water ice, dust, and trace molecules such as OCS were present. But CO2 was by far the dominant feature. The ratio of CO2 to water vapor was roughly 8:1, among the highest ever observed in any comet. That single fact forced astronomers to rethink how this object had formed and evolved. To see a comet so heavily skewed toward carbon dioxide outgassing was to encounter a relic unlike any from our own solar system. Normally, as comets approach the sun, the sublimation of water ice dominates, lofting dust outward to form their bright tails. But in 3I Atlas, the weak water signal suggested something unusual, perhaps an insulating crust or an internal structure that prevented heat from reaching deeper layers. The water-rich regions might remain frozen, while CO2 and CO, which sublimate at lower temperatures, drive the activity. The balance of dust, gas, and ice in the coma becomes a fingerprint of its history, likely echoing the environment of a stellar nursery far different from our own. Even the structure of the coma revealed subtle hints. Enhancements in the sunward direction showed stronger outgassing where sunlight struck the surface. Expected, but the sharpness of that gradient carried clues about the comet's rotation and surface geometry. The broad spread of gas emissions suggested that activity wasn't confined to narrow vents, but released across wide regions. The shape and brightness encoded a hidden map of internal fractures, pressures, and the insulation it had experienced over eons. Webb's observation was far more than a chemical survey. It was a bridge between our solar system and the unknown regions this traveler once called home, between the physics of formation around distant stars and the processes unfolding near our sun. If 3I Atlas had formed near a CO2 ice line in its native system, then its birth environment must have been drastically different from ours. That difference helps constrain how protoplanetary disks evolve, how volatiles migrate, and how planetesimals assemble under varying stellar heat. For the first time, we held direct data, not conjecture, from a comet that had traveled light years to deliver a chemical message from another world. The image renewed the importance of high-resolution infrared astronomy in studying interstellar visitors. Earth-based telescopes and even Hubble struggle with background interference and limited sensitivity, especially at long wavelengths where many molecular signals lie. But Webb, operating in the silent cold of space, with unparalleled infrared sensitivity, could detect faint spectral lines, distinguish overlapping molecular features, and map flux across fine spatial scales. Its success strengthened the case for future missions dedicated to small bodies, interstellar travelers, and the far reaches of the solar system. Pointing and tracking such a faint, fast-moving object was no small feat, yet Webb proved it could be done. And within that success lay something even deeper, a glimpse across cosmic time. If 3I Atlas is as ancient as models suggest, it may predate major epochs of galactic evolution. Some estimates place its origin in the Milky Way's thick disk, making it billions of years older than our own solar system. It has spent eons adrift through interstellar space, enduring cosmic rays, stellar encounters, and the slow erosion of its surface. The ices and materials now visible are survivors, unaltered relics preserving the chemistry of an ancient environment. When we look into that coma, we're peering into matter that has remained frozen for eons, carrying within it a chemical memory from a world that no longer exists. Webb's image is a time capsule, an archive of molecular heritage from a distant star system. As 3I Atlas continues its path through our solar system, its journey becomes an opportunity to watch a transformation unfold in real time. When Webb captured it, the comet was about 3.3 astronomical units from the Sun, roughly 3 times the distance from Earth. As it draws closer, solar heating will intensify, and new volatiles may begin to sublimate. The ratio of gas to dust may shift. Though Webb's observation window is limited, combining its data with Hubble, Sphere-X, and ground-based telescopes can help trace how the comet evolves. New molecular species may emerge. Emission balances may change. Minute details, how fast the coma brightens, how its flux patterns shift, how its tails develop, will reveal clues about its thermal conductivity, internal layering, and fragmentation behavior. Webb's first snapshot now serves as the benchmark. From here, every future observation will be measured against it. The phrase, first real image, carries more meaning than prestige. Earlier telescopes had imaged 3I Atlas, but mostly in visible wavelengths, with limited sensitivity and poor spectral resolution. Webb's infrared reach transformed what would have been a picture into a multidimensional dataset, spatial, spectral, and chemical all at once. Previous images were like impressionist sketches. Webb delivered a vivid, high-fidelity portrait. It didn't just outline the coma. It ventured inward, revealing gradients, internal textures, and faint chemical whispers. This wasn't incremental progress. It was a leap forward in our ability to study such fleeting visitors. That leap demands careful interpretation. The nucleus remains hidden within the haze, its precise size uncertain. The relative abundance of some molecules is still unclear, and models of heat flow are complex. Yet, even with these uncertainties, Webb's image opens a door into previously uncharted territory. Theorists now refine models of outgassing, rework scenarios of ice layering, and simulate the thermal evolution of interstellar comets. It provides a foothold where once there was only speculation. Its implications stretch beyond this one object. Webb's success proves that interstellar comets can be studied, not just spotted and forgotten. Future discoveries could be tracked from the moment of detection. Imagine spotting a new interstellar traveler, immediately turning infrared telescopes toward it, scanning its chemistry, and even planning rapid missions to intercept it. Interstellar objects may soon shift from being rare anomalies to active subjects of study. 3I Atlas marks that transition, a moment when interstellar exploration becomes systematic. The wealth of information from Webb's image also underscores the importance of collaboration. No single instrument can tell the whole story. Webb's infrared precision complements visible light imaging, ultraviolet spectroscopy, radar studies, and in-situ missions. The first real image stands out not because it exists alone, but because it fits into a growing network of global observation, each piece contributing to the puzzle of where this traveler came from and where it's headed. The capture of 3I Atlas is a signal to the scientific community: be ready. Let telescopes stand poised. Let mission planners prepare strategies for future rendezvous. Let simulations run in anticipation. When the next interstellar visitor arrives, we must be ready, not by chance but by design. Webb's triumph is more than a technical achievement. It's a promise, a beacon for the next age of cosmic discovery. The image of 3I Atlas opened a door. Now we step through it, into a realm of mystery built on data, where questions multiply like the particles of dust spiraling off its surface. This was only the beginning. Even the physical dimensions of 3I Atlas invite intrigue. Based on August observations, its diameter could be anywhere from 1.4 to 5.6 kilometers. That uncertainty matters. A larger body means more surface area for sublimation, greater internal insulation, and deeper heat penetration. A more massive nucleus could resist the recoil from gas jets, which might explain why 3I/Atlas shows almost no measurable non-gravitational acceleration despite its evident activity. It's a paradox, dynamic, yet seemingly inert. Its orbit only deepens the mystery. 3I Atlas follows an extreme hyperbolic trajectory, one of the most dramatic ever recorded. It isn't just passing through. It's cutting across the solar system at a speed that defies the sun's gravitational grasp. Its inbound direction traces roughly towards Sagittarius, but finding its exact birthplace is nearly impossible, like tracing a single raindrop back to the cloud it fell from. Whatever gravitational event expelled it from its home system must have been violent. A close stellar flyby, a planetary ejection, perhaps even the influence of a binary companion. Interstellar comets are not wanderers. They are survivors of chaos. What makes 3I Atlas even more unusual is how early it became active. Most comets remain dormant until they approach within Jupiter's orbit. Yet this one began outgassing far earlier, well beyond where sunlight should have had any effect. That early awakening implies that low-temperature volatiles, carbon monoxide, carbon dioxide, nitrogen, or other exotic ices, began sublimating in the faintest warmth. It behaves like a fragile crystal responding to a distant spark. Sustaining such activity for so long, without depleting its volatile reserves, suggests deep internal stores or mechanisms that expose fresh layers, fractures, cryovolcanic vents, or shifting regolith. The chemistry, confirmed by Webb and other observatories, is extreme. The CO2-to-water ratio of roughly 8:1 stands among the highest ever seen. Add to that faint detections of CO, water ice, and trace species like OCS, and you have a molecular composition unlike any typical comet. This imbalance may reflect the environment in which it formed, a region rich in CO2, or one where water ice was stripped away by radiation over eons, leaving a carbon dioxide, heavy residue. The chemistry itself may be a signature of its long-lost home star. Webb's data also reveal the structure of the coma. The gas doesn't stream from narrow jets, but from broad, sun-facing regions, implying layered sublimation zones or networks of fractures feeding the emission. The coma smooths out over distance, blending these sources into a diffuse glow. Within that blur lies data about how deep heat penetrates, how gas diffuses, and how dust interacts with it. By analyzing the brightness profile, astronomers can estimate gas velocity, density, and diffusion rates. The dust, meanwhile, tells its own story. If it drifts gently, grains may be large and cohesive. If it scatters widely, fragmentation or turbulence may be at play. Webb's spectral range from 0.6 to 5.3 micrometers captures many crucial molecular fingerprints: CO2 around 4.2 m, water near 2.7 m, CO near 4.7 m, OCS at 4.8 m, and other organics deeper in the infrared. The strength and shape of these lines reveal temperatures, molecular densities, and even vibrational energy states, helping scientists separate colder gases from warmer ones near the nucleus. If Webb's resolution proves high enough, it might even hint at isotopic ratios: carbon 13 to carbon 12, oxygen 18 to oxygen 16, deuterium to hydrogen and water. These signatures are vital tracers of a comet's birthplace. If 3I Atlas displays exotic isotopic values, it would confirm a foreign origin. If not, it might suggest that the chemistry of life's building blocks is more universal than we imagined. Other observatories have joined in this cosmic collaboration. Hubble imaged the comet on July 21, 2025, about 277 million miles from Earth, revealing a teardrop-shaped dust cocoon surrounding the nucleus. Ground-based observatories like Gemini North and South have tracked its tail, while the TESS telescope helped identify earlier faint detections of the object, tracing its activity farther back in time. Together, these datasets form a mosaic, a coordinated effort to reconstruct its journey. As 3I Atlas approaches perihelion, uncertainty grows. From Earth's perspective, it will soon pass behind the Sun, disappearing from view during its most volatile phase. That hidden interval may conceal eruptions, fragmentation, or sudden shifts in its emission. When it reemerges, only comparison to Webb's original image will tell us what changed. It's like watching a performer vanish behind the curtain at the height of a play. The mystery deepens just when the story turns. That's why Webb's image matters so much. It's the benchmark, the baseline, the moment we caught an interstellar visitor in perfect clarity before it disappeared into the glare. What happens next will unfold against that backdrop. A cosmic drama still being written, carried on a fragment of another solar system passing through our own. And as we study it, one truth becomes clear: this image was only the beginning.